Okay, now let's get into some calculus. So we are going to start off by looking at the most basic law of differentiation. And we'll come back and explore what differentiation is a little bit later. But the actual process of differentiating is a really simple algebraic process. In fact, for some of you, I even showed you how to do this when you were way back in year 7. So some of you may actually remember doing this because really it's just an algebraic pattern. So in very basic terms, when we are finding the derivative, or if we're being asked to differentiate, which is what this first example down the bottom is asking us to do, then we're being asked to find the function before the one that we've been given. And basically that means it's the function that has one less power than the one listed in the question. So, as an example, if I gave you y equals x squared, then the function that would be its derivative needs to have x with a power of 1. Okay, 1 less power than the original function. But you'll notice that I've written a 2 on the front of it. So this is our basic law of differentiation. And it says to us that when we are finding the derivative, then we are going to multiply the entire function by the original power. So that original 2 gets multiplied on the front, and then we are going to subtract 1 from that power. So the 2, we take 1 away, and we end up with 1. So as a rule, this box here shows us what it looks like. And it starts off with some notation. So this d over dx here is actually the notation we use for the derivative. But there are multiple versions of this notation, and it depends on how they write the function's notation for you to begin with. So if you see d over dx and then a function inside the brackets, then that's telling you as a question to differentiate whatever function is sitting inside that set of brackets. The next way they might write the question is by giving you the function in terms of y first. So saying if y is this function, then find the derivative of y with respect to x. And lastly, sometimes they'll use that function notation. So the function of x is equal to some expression. And then they'll ask you to find f dash of x. And that means find the first derivative. And this is hinting to us that we can actually do this process multiple times. So sometimes there are multiple derivatives that can be found for a particular function. But this is the 3 different ways that they may write the notation telling you that they want you to differentiate the function in front of you. So we need to be familiar with all 3. But no matter how they write the question, the process is that simple. So for this first example, all we want to do is bring this power of 2 down the front of our entire function and multiply it on. So we want 2 multiplied on to 3x, but before we write the power down, we need to subtract 1 from it. So 2 minus 1 gives me a new power of 1. And then I look to simplify whatever I end up with. So 2 times 3 gives me 6, x, and I don't need to bother writing the power of 1. And that is my derivative of 3x squared. So before we move on to the next lot of examples, I do want you to copy this down into your books, including the notes on the derivative notation, and then we're going to explore some more examples. Okay, so we have a whole page of functions here, and for every single one of them, we are being asked to differentiate. That is our key question verb. So we are going to apply this process to every one of these functions. starting with question B. Now question B, it has an imaginary power of 1. So really what we're doing is bringing that 1 down the front, multiplying it onto the entire function, and before we write the power down, subtracting 1 from it. So 1 minus 1 gives me 0. And as we go to simplify this further, remembering that anything to the power of 0 is a 1, but that there is also an imaginary multiplication symbol in between that 7 and that x, I really have 1 times 7 times another 1 simplifies all the way down to 7. In question C, I have 2 terms that I need to differentiate. And as we add more and more terms onto our function, we need to differentiate each term separately. So I'll start by bringing this 3 down the front, multiplying it onto the x, and taking 1 off that power, and then do the same thing for the next term. Bring the 4 down the front, multiply it onto the x, take 1 off the power. Question D is exactly the same. So we're going to bring this 4 down the front, multiply it on the x, take 1 off that power. Bring that 3 down the front, multiply it onto x, take 1 off the power. And then for the last term, there is no x value with a power attached to bring down the front. But that's because really what's sitting behind this 5 is an x to the power of 0, or no x value. And as we bring that power down the front, we have 0 multiplied onto the original function. And this is where I'm going to stop, because remembering that 0 multiplied onto anything is just 0. So that final term is going to disappear completely. And so it's only the first 2 terms that end up in my derivative. For question E, same idea. We're going to bring that 7 down the front, multiply it onto the existing function, but take 1 off the power. And then we're going to neaten that up. And then we'll notice that in question 2, they're using that function notation. And they're saying to us that if this is our function, that they want us to then evaluate, so find a numerical answer, when we substitute -1 into the derivative. So the first thing we need to do is write out what that derivative looks like, and I'm going to use the correct notation for the function here. Each term I need to do separately. So I'm going to start with 2x to the power of 5. So bring the 5 down the front, multiply it onto the function, take 1 off the power. Bring the 3 down the front, multiply it onto the function, take 1 off the power. Remembering that this has a power of 1, so bring it down the front, take 1 off the power, and this constant term has an x to the power of 0, which means that I'm going to multiply by 0 and it's going to disappear. So now I'm going to neaten it up so that I can see what my derivative expression looks like. And then they're asking me, everywhere I see an x value, substitute -1 into it. So I'll have 10 times -1 to the power of 4 minus 21 times -1 squared plus 5. And I can now evaluate that expression to a final answer of -6. Okay, question 3 is a little bit of a problem because we don't have separate terms here that I can easily differentiate. I have this division that's sitting here by 2x, and this is where our index laws are going to come into play. So there is a trick we must always remember when we are differentiating, and that is that we must always have our functions written in index form first before we can find the derivative. So that means that I'm going to apply law 2 here and actually divide those same bases of x so that I can simplify this expression. I'm also going to split this fraction up into its two separate numerators so I can see how those x's are going to divide and cancel down. So in the first one, x squared divided by x is going to give me 3 on 2x, and then x divided by x cancels and leaves me with 5 on 2. And now if I want to go and differentiate that expression, I have two separate terms, both with their own powers, that I can go and find the derivative for. So my derivative is equal to, bring this power of 1 down the front, multiply it onto the whole function, take 1 off the power, and this next one has an x to the power of 0 sitting behind it, which means that I am multiplying by 0 as I bring that 0 down the front. And so all I'm left with is 3 on 2 as my final derivative. And question 4 is really not as tricky as it looks. This question is asking us to differentiate this expression with respect to r. So that means that we're only considering the powers that are sitting on r. Anything else we're just treating as a separate value. So to differentiate with respect to r, I'm going to bring r's power down the front. So the first one is a 2. Multiply it onto everything else that's sitting there and take 1 off that power. And then bring the next power of r down the front, which happens to be a 1. Multiply it onto everything else that's sitting there, except for that r, I'm going to take 1 off its power. And then we're going to simplify and neaten up this expression. So 2 times 2 is 4 pi r, plus 1 times 2 is 2 pi h, and r to the power of 0 goes to 1. And for these final two examples, again, remembering that we must have our function written in index form before we differentiate it, well, we can see that these two examples are definitely not written in index form. They look like some of our index law answers, and so we need to apply those indice laws first before we differentiate. So this first one, we're going to apply law 6 to rewrite this surd, and the second one we will apply law 5 to rewrite this fraction. So question 1 written in index form would be 7 multiplied onto x to the power of 1/3. So that's what my function looks like in index form. And as I go to differentiate it, I'm going to bring that third down the front, multiply it onto the existing function, and then take 1 away from that power. So now I have, well, 1/3 times 7 is 7/3 x, and 1/3 minus 1 is -2/3. So now I actually have a negative index, which means that I can simplify this even further by putting that x in the denominator. And remember that when I do that, I take that negative off the power because I've used it, And now to make sure that my answer matches the format the original question was in, I also need to use that power index to rewrite the surd. So I have a 7 sitting in the numerator, I have 3 in the denominator, and then I have x to the power of 2 and a third. And really, that's the same as having the cube root of x squared. And that's my answer fully simplified. For question 2, we're going to start by rewriting this function in index form so that x squared is really an x to the power of -2. Then we're going to differentiate. So I'm going to use the notation. They gave me the function in terms of y. So I'm going to differentiate y with respect to x. I'm going to bring that -2 down the front, multiply it onto my entire function, but one more off that power. And so this time you'll notice that it ends up more negative. And so that I match my original question format, I am going to use my index laws to rewrite that back in its reciprocal format. Okay, so that is the basic function or the basic pattern that we use when we are differentiating. And so this little summary, it would be a good idea if you now pause this video and write the summary down in your book, because these are the things that we need to remember as our functions start to become more complex and we need to start expanding on this law of basic differentiation. So our basic differentiation pattern is that we will always multiply that entire function by the original power and take one away from the power. We do this to every single term in that function separately until there are no more terms left to differentiate. If the function is already a constant, so that means a number that's sitting by itself, then we saw that the derivative of that term goes to 0. If that constant is already a 0, well, it's still going to give back a derivative of 0. It still has an x to the power of 0 sitting after it, and 0 times 0 still gives us 0. So the derivative will be itself. And if the function is not written in index form first, then we must rewrite it before we differentiate so that we can see what each of our separate powers are. Okay, so give the worksheet a go and see how you go. The more you practice these, the more comfortable you'll become. And as long as you're remembering that this is just a pattern and we are doing the same thing every time, make sure it's in index form first and then bring the power down the front, take one off the power to every single term you see sitting there. And once you've done that, simplify it using your algebraic techniques as much as you can.